Hello, this is the first of several supplemental lectures to this course on understanding ABGs. These supplemental lectures are going to focus on topics that are not essential for common ABG interpretations per se, but which may simply be of interest to people who have already shown interest in abnormalities of acid-base balance or gas exchange. As you can see, the specific topic of this lecture is the derivations of the equations of gas exchange. The learning objectives of this lecture are to be able to derive the alveolar ventilation and alveolar gas equations from basic principles, and to be aware of some of the alternative forms of the alveolar gas equation. Regarding the basic principles from which these equations are derived, they both depend upon Dalton's law and the conservation of a particular gas. The alveolar ventilation equation is specifically based on the conservation of carbon dioxide, while the alveolar gas equation is based on the conservation of oxygen. The first thing to review is Dalton's law. John Dalton was an English chemist and physicist who laid much of the earliest groundwork for modern atomic theory, and in this groundwork was the law of partial pressures, more commonly referred to today as Dalton's law. Although Dalton discovered this equation empirically, it was later shown that it could be mathematically derived from the kinetic theory of gases. It states that the total pressure of a mixture of gases is equal to the summation of the partial pressures of each individual gas. If the summation sign notation is unfamiliar or intimidating, this can also be represented as such. For the purposes of respiratory physiology, there are normally only 4 gases present in significant quantities in the lungs. Thus, barometric pressure, commonly notated as P sub B, is equal to the sum of the partial pressures of nitrogen, oxygen, carbon dioxide, and water vapor. In the absence of applied positive pressure, such as would be seen by a patient on a mechanical ventilator or BiPAP, barometric pressure is equal to inspired pressure, denoted as P sub I. A corollary to Dalton's law can be quickly derived from simple algebra that the partial pressure of a gas X is equal to the fractional concentration of that gas multiplied by the total pressure. For example, the partial pressure of carbon dioxide in alveolar gas is equal to the fractional concentration of CO2 in the alveoli times the total intraalveolar pressure, and the average intraalveolar pressure must equal barometric pressure. So now let's talk about the alveolar ventilation equation, which allows one to calculate the partial pressure of CO2 in arterial blood as a function of barometric pressure in alveolar ventilation. As I already mentioned, this equation is based on the conservation of CO2. In other words, the rate of CO2 production by the body must equal the rate of CO2 elimination by the lungs. The rate of CO2 production is denoted as V dot CO2. In this case, the dot notation, sometimes referred to as Newton's notation, refers to the derivative as a function of time of whatever variable sits underneath the dot. In this case, for example, the dot sits over V for volume. The time derivative of volume is flow, or in this case, the rate of gas production. So V dot CO2 equals V dot big A, which is the rate of total gas flow from the alveoli, which is another way of stating the alveolar ventilation, multiplied by the F big A CO2, or the fractional concentration of CO2 in alveolar gas. From Dalton's law, we know that P big A CO2 equals P big A times F big A CO2. Therefore, using substitution, we can say that V dot CO2 equals alveolar ventilation times P big A CO2 divided by intraalveolar pressure. As has been empirically demonstrated, in humans alveolar CO2 is in equilibrium with arterial CO2. That is, there is no AA gradient with respect to carbon dioxide, even in most pathologic states. Therefore, P big A CO2 is approximately equal to P little a CO2. So we'll make a simple substitution like so. Simple algebraic rearrangement leads us to this. P little a CO2 equals the rate of CO2 production by the body times the intraalveolar pressure, which is normally equal to the barometric pressure, divided by alveolar ventilation. Turning to the alveolar gas equation, which was originally known as the alveolar air equation, it is a means to calculate the partial pressure of alveolar oxygen, from which we can calculate the AA gradient. Its derivation utilizes the fact that the net rate of oxygen entering the lungs must equal the rate of oxygen consumption by the body. The net rate of oxygen entering the lungs is equal to the oxygen inhaled, which is alveolar ventilation times the fraction of O2 in inspired air, minus the alveolar ventilation times the fraction of O2 in alveolar air. This is equal to V dot O2, which is the rate of oxygen consumption by definition. It's critical to realize that the FiO2 in this equation is not exactly equal to the FiO2 to which we commonly refer. This FiO2 is not the fraction of oxygen in the air that is breathed in through the nose and mouth, but rather the fraction of oxygen in the air once it reaches the alveoli. We will denote this with a red star. The reason for this difference is that both ambient air and medical oxygen is relatively dry. However, before it reaches the alveoli, it becomes saturated by water vapor that is picked up within the respiratory tract. By Dalton's law, if some of the total pressure is occupied by water vapor, there must be an equal decrease in the other gases present. Since this decrease in each of the other gases is proportional to the relative concentration of water vapor, FiO2 star is equal to FiO2 times the total pressure of inspired air, or P sub I, minus the partial pressure of water vapor, all divided by P sub I. We'll need to come back to this definition of FiO2 star at the end of our derivation. From this first step, we'll factor out the alveolar ventilation. Then we'll use the definition of the respiratory quotient. If you remember from lecture 16, the respiratory quotient is defined as the ratio of the rate of carbon dioxide produced by metabolism to the rate of oxygen consumed. The respiratory quotient can be measured for an individual patient, but this is an extremely cumbersome task and instead is usually assumed to be 0.8. Another supplementary lecture discusses the respiratory quotient in more detail. With some substitution, we'll replace V dot O2 with V dot CO2 divided by the respiratory quotient. Remembering from our derivation of the alveolar ventilation equation, V dot CO2 equals alveolar ventilation times the fraction of CO2 in alveolar gas. So we'll substitute that in and we get this, and of course the alveolar ventilation on both sides cancels out. We are now left with FiO2 star minus F big A O2 equals F big A CO2 divided by the respiratory quotient. And after another simple rearrangement, the equation's form is starting to look a little more familiar. We are going to bring in Dalton's law once more and substitute for the F big A O2 and the F big A CO2. Multiply everything by the total alveolar pressure. Now we're almost there. Just substitute in the expression for FiO2 star to get this. Since the total inspired pressure is equal to the average total alveolar pressure, these two variables cancel out. This leaves us with the familiar form of the alveolar gas equation. I'd like to review two other forms of the alveolar gas equation. First, with some algebraic manipulation of the common form, we can restate this equation as the partial pressure of oxygen in the alveoli equals the partial pressure of oxygen in inspired air minus the difference between inspired pressure and water vapor times the ratio of oxygen consumption to overall alveolar ventilation. Although more awkward to use in practice, in form this actually makes more intuitive sense, as one can restate it as the amount of oxygen in alveolar gas is what remains after the oxygen used for metabolism has been removed from the oxygen in inspired gas. The second alternative form acknowledges that because the rate of O2 consumption exceeds CO2 production, additional air passively enters the lungs during respiration that is in addition to active alveolar ventilation. I won't go through the somewhat tedious derivation that accounts for this effect, but here is the final result. It's the same as above with the exception of a lengthy additional term thrown onto the end. Luckily, although it technically makes the alveolar gas equation more accurate, this additional term is too small to be clinically relevant. For example, for a patient with normal respiratory physiology breathing room air, this final term equals 0.21 times 40 times 1 minus 0.8 divided by 0.8. This equals a minuscule 2.1 millimeters of mercury. Compare the magnitude of this to that of the first term, which is normally 150, and the second term, which is normally 50. Therefore, for all practical purposes, this last term can be ignored, reducing the complete form back to the common form above. Finally, there are several assumptions to briefly mention that are required by these derivations. First, gases must obey Dalton's law. Modern physics has demonstrated that Dalton's law does not exactly describe the properties of real gases at high pressure, though the differences seen at typical barometric pressure are inconsequential. Second, alveolar gas is saturated with water vapor. This assumption is completely valid. Third, carbon dioxide in the alveoli is in equilibrium with carbon dioxide in the pulmonary capillaries. That is, P big A CO2 must equal P little a CO2. This holds to be valid in all but the most extreme of pathologic processes. And finally, inspired gas contains no carbon dioxide. With our atmospheric concentration of CO2 at less than 0.1%, this is close enough to be true in all medical situations, but may not hold true in experimental situations or other very unusual circumstances. So that's it for the derivations of the equations of gas exchange. I hope you found this course supplement interesting. The remaining supplemental lectures will cover topics such as what factors can influence the respiratory quotient and how to interpret ABGs at high altitude.